So far in this topic, we've only looked at one type of electricity, current electricity. We know that an electric current is just a flow of charges, so current electricity is the study of these moving charges. As you might have guessed, the other type of electricity involves charges which aren't moving, and for this reason we call it static electricity. Think stationary. It's a real pity that we can only spend one video on static electricity, since it can explain how so many cool things work, from lightning strikes to why we have to delint some of our clothes. But at the very least, over the course of the next few minutes, you'll get everything you need to electrify your exam efforts for this topic. You might already know that solids, liquids and gases are composed of atoms, and that these atoms are made up of protons, neutrons and electrons. The protons and neutrons in an atom are located in its centre. Together, they make up its nucleus. The electrons, on the other hand, orbit the nucleus like this. You might also know that the protons have a positive electrical charge, the electrons are negative, and the neutrons, as the name suggests, are neutral, which means that they have no charge. Some types of materials are very good at transferring charges through them. We call these materials electrical conductors. Metals tend to be very good at conducting electrical current because some of the electrons they contain are not strongly bound or attached to any particular nucleus, which means that they are free to move from one end of the metal down to the other. You may know from your GCSE chemistry studies that these are sometimes called delocalized electrons. It's difficult for some other types of materials to transfer charges through them. These are known as electrical insulators. In general, non-metals fall into this category. What this all means is that any extra static charge which we add to an object is more likely to hang around for a while if it's made from an insulator rather than a conductor. A very good question to ask at this point would be, but how do these static charges build up on an object? Well, you could turn off your computer or set aside your tablet or phone and ponder this over till your heart's content. Or you could sit back for the next few minutes and do absolutely nothing other than listen to the sound of my voice. So here goes. There are actually a number of different ways in which we can place extra charges onto an object, but the most important one for you to know for your exam is charging by friction. You probably already know that friction is a contact force which opposes motion. When you rub your hands together, for example, friction is the name of the force that limits their speed and causes them to warm up. But just how can this force charge an object? If you've ever bent a stream of water with a comb, or rubbed a balloon on your jumper and stuck it to a wall, or heard a crackling noise when putting on a nylon t-shirt, then you've already charged an object by friction. Most of the time, most objects are neutral, like this polythene rod, for example. At the minute, it's neutral because it has an equal number of positive and negative charges. The same goes for this woolen cloth. When they're rubbed together, however, something special happens. Some of the negative electrons from the cloth are transferred onto the rod. Are both objects still neutral now? The answer, of course, is no. The rod now has more negative than positive charges, so overall it's negatively charged. Likewise, because the cloth now has more positive than negative charge, positively charged overall. Seems simple enough, doesn't it? The hawk-eyed among you might be wondering why the charging up of these objects was caused by the movement of negative rather than positive charges, and that will be a very sensible thing to be wondering indeed. You don't need to know about this for your exam, but just in case you're curious, if you think back to the structure of the atom, you'll remember that the negative electrons are the particles that whiz around the positive nucleus. The electron is also a much lighter particle than the positive proton. Both of these facts mean that it's much easier for electrons to zip from atom to atom or from object to object than protons. On now to a bit of old school physics fun. The term electrostatic forces sounds pretty scary, I have to admit, but if we break it down, it's actually not too bad. Electro here just refers to electric charges, and static to stationary, which we know just means not moving. So these are just forces between charges which aren't moving. Everyone knows that opposites attract and likes repel, don't they? But what does that actually mean? When it comes to static electricity, it just means that a positive charge and a negative charge, like these two, will feel a force of attraction toward one another, like this. These negative charges, on the other hand, will feel a force of repulsion away from one another. The exact same thing would have been seen had both charges been positive. That all seems very straightforward and dull, so why should you care about any of this? Well, the reason you should care is that these simple rules can be used to explain how loads of incredible things work, such as this age-old party classic. Have a look at this balloon. Okay, so it's yellow and balloon-shaped and probably made from some sort of rubber, but what else can you tell me about it? Well, if it's neutral, that means that it contains equal numbers of positive and negative charges. When we rub this fine specimen of a balloon on our jumper, electrons are transferred from the jumper to the balloon so that the balloon becomes negatively charged. Good old charging by friction strikes once again. When the balloon is held next to a neutral wall, something different happens. Because the balloon is an insulator, it can't just lose the negative charge it's just gained. But what about the wall? Well, as we discussed just a moment ago, the positive charges are pretty much stuck where they are. The negative electrons on the wall, however, are repelled by the negatively charged balloon and so move away from it. When this happens, we're suddenly left with a section of the wall which is positively charged here. It's the force of attraction between this section of the wall and the negative balloon which allows the balloon to stick to the wall. After all that scary business about electrical safety a couple of videos ago, we're going to go on now to talk about the one device which has doled out more electric shocks in schools over the years than any other, the Van de Graaff generator. In class, you might have used one of these to make your hair stand on end or to send some foil bun cases flying into the air, and you'll find loads of really cool Van de Graaff videos online. But here, we're going to focus on one thing: how the Van de Graaff generator produces lightning in the lab. Before we go on to look at how a Van de Graaff generator actually produces a spark, we'll have a quick look at its main components. The two small round bits here in the diagram are the rollers. When they spin around, the belt moves up and down the device, and as it does so, it puts a charge onto the dome at the top. When the discharge sphere is brought close to the dome, as you might know, sparks can be seen. And at the very bottom here, we have a connection to earth or ground. Thankfully, you don't need to know the ins and outs of how one of these things works for your exam. They're actually a bit tricky to explain. What you do need to know though, is that when it's running, a large charge will develop on the dome of the Van de Graaff. Whether this charge is positive or negative depends on the actual design of the device we're using. Let's say here though, for the sake of argument, we're using a Van de Graaff which has a positively charged dome. We know that if we get too close to the dome when it's charged, we can receive a really nasty electric shock. But why? Don't worry, I'm not going to ask for any volunteers here. Instead, we're going to use the earthed discharge sphere to find out what's going on here. Before the Van de Graaff is turned on, the discharge sphere will be neutral. In other words, it will have no overall charge. When the sphere is brought close to the running Van de Graaff generator, however, extra electrons will rush up along this cable, and there'll be a buildup of negative charge on the side of the sphere closest to the positively charged dome. Remember that this all happens because opposite charges attract. If the positive charge in the dome builds up to a high enough level and the discharge sphere is brought close enough to it, a spark will leap across the air gap between both objects. During this spark, electrons will flow towards the positive dome, reducing its overall positive charge. It's for this reason that it's called a discharge sphere. If you're ever unlucky enough to receive a shock from a Van de Graaff, you are the discharge sphere. The current which flows between the dome and Earth through you causes the dome to lose excess charge and move closer to being electrically neutral. Exactly the same thing happens in a thunderstorm. When the lower part of a thundercloud becomes negatively charged, the ground below will in turn develop a positive charge. If the amount of charge builds up to a certain level, there will be a spark between the cloud and the ground. Lightning strikes. You see? What other subject could explain how lightning works? If you'd like to know more about the charges that make this, bending water and sticking balloons to walls all possible, have a look at the next video, which is on the topic of electric fields. Thanks for watching.